So everyone, yeah, so thanks. We're happy to have Chuang Gan to give a talk. So he's a faculty at UMass Amherst and a research manager at MIT-IBM Watson AI Lab. And then I'll just say that he's done a lot of great research at the intersection of computer vision, AI, cognitive science, and robotics. And I guess we're excited to see what he'll talk about today.
All right, thanks for the next introduction. I'm very excited to be here. Actually, this is probably my first equal talk, so I'm very excited here. And my main area is most on computer vision and AGI, and with application on robotic learning. And the thing we are doing actually is called, let's see, called Genesis. How many people have heard about this one? Okay, that's great. So basically, in today's talk, I will mostly talk about the roadmap that how we are working actually 5-6 years ago, and how we can reach on this kind of Genesis simulator. And the goal here is most about trying to build that kind of very unified and combined with generative AI that can be broadly useful for robotic manipulation. Okay, let's start with the video. Actually, this is my daughter Caroline. So she's playing a popular game called Circle Puzzle. You can see that even they have never taught her how to play this game before. She knows that how to play this game and also make some attempt, and then finally she can make the task very, very successfully. The thing here is that why she can succeed in this task, that from cognitive side, actually there are many studies show that even the kind of 15 months baby here, she has the basic knowledge about objects and also the affordance, how to interact with them. And then Caroline can using her mental model to plan action to achieve the task. So this is how the kind of 15-year-old baby can do. And the question here that we have seen a lot of the kind of large language model, VLA, that all the kind of pet zero, is this the most powerful embodied agent today has intelligence at the level of Caroline? So the answer may be yes, because we have seen tremendous progress in robotics today, right? We can see that we can using the kind of airflow, the user tool to do that kind of that kind of close manipulation. We can teach this robot that play that kind of soccer as flexible as human. And we also have using large language model can do some personalized that kind of tidy robot can help you do some chores. We can also play this kind of we can also use two arms to play this kind of catch and play and catch this kind of game, right? We might have assumption, okay, we already have achieved this kind of very general purpose intelligence. But I would still say that we have the robot intelligence, but not general enough. What do I mean by that one? You may be curious, so what do we mean by the generative agent? Obviously, it's general purpose robot. So the definition can be very different, but in general, we are talking about that we have a robot that can take a multimodal input, for example, language, images, whatever that has multimodal input, and can do a bunch of different tasks across the environment. So this is the robot that we hope we can have at your home, in office, in workspace, in healthcare, so many places. Even though we have this very powerful, that's a very powerful environment, but we can see that they still make some mistake. For example, in this case, they will mess up this kind of hooking tool. And also we work on robot, we know that in many cases that we, even though we can create some very beautiful demo, but it always fail as well. So maybe we change a little bit of location, the model will not really generalize. So I have to say that we are still far from this kind of stuff that has the generative agent. In our group, we have been working for a couple of years. Is that we are trying to take inspiration from human cognition and building a thing called the world model that trying to reverse engineering of the model working in both in both human and brain. And then we can build in computational framework that to approximate human mental model and allow us to doing that kind of generalization, that kind of flexible skill learning. So this is the intuition behind the Genesis simulator. You might be say that, okay, there's many things people talk about that can be used as a world model. For example, people talk about, okay, this large multimodal language model can be said as a word model. For example, we give these images, you ask a GPT-4, they can actually predict what happens next very accurately and in a decent job. They can say that this egg actually will likely fall due to gravity and might break upon hitting the hard surface below. Okay, he understands the physics very well in this longer format. But how about we ask this kind of very basic physics question? So which ball actually will fall down first? As a human, we can very easily to identify the right side will fall down first. The reason is very simple, because they take the shortest part and also have larger acceleration, right? But we can ask GPT-4, so GPT-4 we can say that, okay, both balls will reach the ground at the same time. Okay, he still makes this kind of very simple common sense question. Even though you ask them why he can explain them, so the physics knowledge behind them very in a decent way, you say that there's force acting the balls on gravity, which put down to the same acceleration. So here make a fact mistake. But if you look at the longer is right down, actually it's very accurate. But it doesn't necessarily mean that they understand the physics world as we human do. And a more popular definition of word model is probably came from the kind of software that people talk about. Okay, large video model can be a word model because it can generate that kind of very photorealistic video and follow the physics principle in a nice way, right? But you probably also have seen many very interesting demo here. Right? When they're doing that kind of fluid manipulation, actually the physics is not correct. And here, when they do collision, actually they also have that kind of manipulation. And here the running actually not easily follow the physics principle. And also this kind of very simple pick place task, the chair will just fly away. So I would say that even the video model, we recently have made many good progress. That's kind of Thorough tool, or that kind of Google has that kind of Gemini, that they make tremendous progress. But we'll still say that they are still make some very simple physical mistake. This can be the data problem, but also can be the method problem. Okay. So in our group, I believe that the best way to model the physics world is to bring the best of the world. So the idea we have that how can we combine the power of generative AI, this kind of large foundation model, with the first principle built already in the physics engine. So our idea is we're trying to combine the generative AI and the physics engine and building that kind of powerful word model to approximate human mental model. This is the way we define as generative physics simulation. Okay, to start with, maybe we can to see the necessary of we need a physics engine to do the reading. Maybe let me take a small question here. So look at these images. Tell me that which object is heavier. How many people think the gray sphere is heavier? Yeah, the gray one heavier. So how many people think is sorry? So the first question is the gray. The second question is the green. So who thinks the green sphere is heavier? Okay, many people not raise hand because you feel very confusing, right? But how about show a video here? This sphere is heavier. How many people think the gray one? Yeah, it's very obvious because we have the kind of mental model we infer from physics. We leverage the physics knowledge, that kind of conservation of momentum. We can infer the physics property here, right? Actually, human running that kind of mental model, so in our mind to do that kind of physics reading. So this actually is a very fundamental problem in robotics as well that called system identification. We're trying to identify the parameter of the physical object we're trying to interact with. So the idea here that we're trying to leveraging a differentiable physics engine to perform that kind of system identification task. The idea is very simple. So for people not very familiar with simulation, I can give a very quick introduction. So simulation essentially is that you give current state S, T, and also the physical parameter of object, and then you run for a path that you will know what happened next. And by continuous process, actually you are doing the kind of, we call it physics simulation. And the interesting part of differentiable physics simulation is that, so basically, so the idea of using parameters to do the parameter estimation is that You basically run the physics simulation, you render images, you compare, you render, so sorry, your given current state, you're doing forward pass, you have the next state, you compare the current state and next state, and trying to minimize the difference. And then you can using the gradient descent to estimate the best parameter. So the idea is that if you can, if you want to estimate the failure parameter, and the simulated result batch match the observation means that you estimate the parameter is correct. How can we efficiently solve this problem? This is the idea of differentiable fields simulation trying to do. So we can make the whole physical process differentiable using that kind of Tai Chi programming, language written by Yuan Minghu. So we can make the full physical process differentiable, and then we can using the gradient during the backpropagation, just like you training the neural network to get the optimal physical parameter very efficiently. So this is the basic idea. We're using different physics doing this kind of parameter estimation. Now here is the result. On the left side is a real-world video, and we can we can actually reconstruct the physical parameter and the metadynamic using this approach. So on the right side is the simulation result. And you may be curious that how this kind of approach that today we are the deformable object manipulation workshop. So how can this kind of simple approach apply to much complex shape, for example, articulation and the kind of solve body scenarios? So exactly the same pipeline. So the idea we have that we can render an image here. Then you can compare with the rendered images with simulated images, and then you're using another perceptual laws to compare the difference of the rendered images and use that as estimation whether the state of match or not. So, and again, because we have that kind of differentiable simulator combined with the differentiable rendering, the idea that you have a physics engine, you have a rendering, you basically can use the physics simulation and rendering, generating the dynamic videos. And then you compare your render result and also what you observe. You can use that the difference of the simulated result and the real world observation as the training signal, and leveraging the kind of both differentiable physics engine and different rendering doing backpropagation, estimate the physics parameter correctly. So as a result, here is a quadrilateral example we have, right? So the left side actually is the real world video observation. On the right side, actually we can reconstruct the result, the action sequence in the simulation in a very accurate way. And because we are deformable object, right? So how about that kind of object that you don't really have the shape, you don't have any physics, so you don't have any geometry prior. How can we do both geometry and the physics reconstruction? For example, we try to estimate the Young's modules of viscosity of this droplet. How can we do that? So the idea we have that we can do this kind of joint estimation by leveraging multiple video. So the idea we have that we combine the neural rendering with different physics, and we can joint optimize the geometry and the physics parameter together using the the training signal is that we render the multiple images and matching the multiple observation, and we using this simulation we can reconstruct both geometry and the physics parameter here. So as a result, we can do the kind of reasonable well, the kind of solid body particle reconstruction, matching their physics and geometry in this way. So this is basically the first part of we have been doing that, how we can take a real world video, take a real world observation, how we can build a digital twin here. And the idea here, we combine the idea of different physics engine and different rendering, use that to reconstruct the physical world. And exactly the same framework, I will, in the second part of my talk, I will most talk about how this exactly same framework, how we can use that one for policy learning. So this we call that differentiable physics for planning. So in the first problem, we introduced that given current state, you have physics parameter, you can run simulation, getting that state. And in the kind of planning task, actually you can also perform action here. Given current state and action, actually you will get that state, and you can continue the process. Since this is a planning task, we can always design a reward function to matching how you perform that matching the desired goal, right? We can design that reward function. And again, using that kind of differential pipeline, we can also optimize the trajectory and getting the kind of open loop policy for arbitrary tasks. So the first application we have been seeing actually is called the kind of pricing live. So the idea that we're building the kind of differentiable phase simulation for the kind of pricing manipulation. So the tasks including the kind of dot manipulation and transform to a shape, and also the kind of noodle pickup so this is that kind of pricing task. And but the key message we're trying to find is here. So we find that on the left side, actually, is we using the kind of different phases based plan. Only around 100 or 200 iterations, we can find an accurate solution very efficiently. But when we're running reinforcement learning, for them, we're running for 100K. Actually, the model is still struggle to understand what the task it is. And then in the left curve, actually, I dropped the kind of learning curve. You can see in the green curve, if you're using different phases doing trajectory, you can learning the skill much flexible and efficiently. So based on this observation, we have been, so this is the first material we have been looking at is the pricing. So based on this observation, we are thinking that there might be a powerful idea. We can leverage the kind of differential physics engine to really revolutionize the robot skill learning. So this is the initial point. So this is the initial point of the genesis. We are trying to building a differentiable physics engine for manipulation that can benefit all the tasks. So at starting point, we play this pricing. And later on, we also finding a very important thing that I want to mention here, because for different phases, you're always getting that kind of open loop planning. So how we can turn it to a closed loop policy. So the idea that in this diff skill paper, we are trying to do is that we're trying to use a neural network, taking the physics engine, generate policy and turning, and then using neural network doing abstraction, and then we can learning a closed loop policy. And also this also the initial idea of what's the role of the physics engine. Etc. For the different physics engine, we see this as a big data engine for the robot learning, for robot foundation model. So this is also the initial point of Genesis, that we need to build a unified and generative data pipeline for robot learning. And since then, we have been working on a couple of different projects. For them, this is a project with Shuran Song that we building a kind of multi-material cutting simulator that they can, based on the defined objective, we can optimize a beautiful trajectory for them in the task. We are trying to cut as much volume as possible, but not hitting the middle kernel here. And we learning the policy in the simulation. So basically we collect a demonstration data set in the simulation, and then we learning that kind of policy in the real world. You can see that the policy can cut various kind of food that even though they are in a different shape, but they can always cut the volume and trying to avoid the middle curve. And beyond the kind of stuff, we have been working that kind of fluid manipulation. And for them, we can make that kind of coffee lattes. We can do some fancy mixing. We can make ice cream. So we are gradually extend the material of the kind of simulation platform. And this is the real world so this is the real world result that we getting the policy from simulation and then transfer to the real world. We also have been in the kind of thin-shell manipulation, that kind of content-rich task. Actually, is the simulation built by my student Ian Wang that sits on at the desk here. And we also thinking about at that time we also think about how we can do the kind of large-scale solve simulation. So this is Unbound solve that we published last year at Colo. So basically, we have some idea that how we can make it much more efficient and can do the kind of self-carrying, that kind of large particle simulation in a relatively fast speed. But till now that we have, I think 2 or 3 years ago, we found that, okay, we are making progress slowly, that we're trying to building a simulator for each material. And the question that, okay, we're working on robot simulation. And at that time, I think a lot of people is question that robot simulation might not be useful because it's really easy. Because first, we don't really have a very powerful unified simulator. And second one, even we have a simulator, so everyone feel very struggle to set up a simulator and define the task, finding the training signal and finding the right algorithm. so this is the fundamental challenging for simulation, how to scale. So I have seen that for a while. So at this time, I think there's the two fundamental questions we have to solve at the time. The first, that how can we build a unified simulation? That so it cannot have a simulation just, okay, that's just for fluid, that's just for plastic, that's just for radius, that's just for rigid, but I want to put them together. There's no simulation there. And the second one is that how we can automate it, building pipeline can propose tasks, set up a scene, and learn them automatically. So this is the question that I've been thinking for a couple of years, and I'm happy that we're making some progress here. So for the first thing, that this is the motivation we building the Genesis. So Genesis, you probably have seen the demo, and we already released the whole simulator. I think in last September, it received a lot of feedback, both positive and negative. It is. So the idea of Genesis is that we're trying to doing a kind of without, I would say it's more like an integration. So we're trying to have a physical simulator. So the motivation is we're trying to have a simulator that can support rigid body, liquid, gas, deformable, elastic, thin shell, granular object, all of them in one simulator. So another thing that we should be careful that we should also solve the problem of multi-material coupling. So the core contribution of Genesis, we're trying to build it. So we're trying to integrate all the existing solver and also solve their multi-material coupling problem. So that will allow us to simulate all the physical so that physical phenomena in the world. So we're trying to remove the barrier. Okay, we're just working on rigid bodies, so or we're just working on some particular material. And other here, we also support a wide range of the robot, including the arm, leg robot, lateral hands, mobile robot, drone, softbot. This is, and also the most important that we implement the full thing from scratch using Tai-Chi. This is a differentiable programming language that can writing out the physical in a differentiable way. And also it's a borrow, so it has the idea that can make the mathematical parallel, GPU accelerated support, and also very easy to deploy using Mac, using in Linux, using in Windows. So this kind of cloud platform uses makes it really easy to use. It's also one of the principles when we building the Genesis. So as a result, you have been seeing that kind of video. We found that we can simulate a bunch of very broad physics phenomena, including particle, rigid, and also we came up with this very photorealistic rendering because we think Genesis is essentially very important to have the kind of data pipeline. So even that here I didn't show too much robot demo, but here I want to show that even you compare with some video generative model, we can also generate the kind of very photorealistic video, the kind of very physics correct data for embodied AI. So once we have the kind of unified agent, we still not solve the second problem. Okay, even you have similar how you can propose task, what the task it is, and even you have a task, how you can set up the scene, and even you have the scene, how you can learn. So this is a couple of problems that is a fundamental challenging to scale up the simulation. So this I have actually proposed a second idea, actually called the robot jam. So the idea of robot jam that with the kind of generative AI, can I using large model, vision long model, or video model to define the task, generate the scene, and also propose the task training signal. With all of them in hand, we probably can automate the skill learning in the simulation. So this is the motivation of RoboJam. We hope to automate everything in simulation. So let's give an example. For example, we are trying to, so basically you have a lot of robot body, and you also have a lot of objects you want to manipulate. We can first, using large model to propose a task. For example, we take this robot arm and this safe. We can ask large model, okay, what task we can do with this robot arm, with this shape? You can say, you can retrieve one gold bar and lock the safe, open the safe door. So the large model can propose a series of tasks in this kind of longer format. And in the second phase, we actually need to generate the scene. So at this time, we're using large model to basically generating the scene layout. And also we either using some type of 3D model or some type of retrieval to find an object. And once we generate scene, we also have this kind of using vision learning model to verify the thing, because a lot of things generative might not be useful. Here, in recently, we have some work that we incorporate the procedure generation and time scaling. So probably we will release the full pipeline by the end of this year. So there's some new idea here to do very reliable and large scale scene generation. But the rough idea here that we're trying to using VLM agent to do that kind of scene generation. And after getting scene that we can, in the surface, we need to generate the training signal. For them, we need to support. So we need to select what kind of training probe we need to have. For them, either using reinforcement learning, task motion planning, or different feed engine that based on different type, we will have that kind of different choice. And we can also generating the reward model, for example, using, so you'll hire everything using language writing reward model, and also using VLM to provide level. So there are a couple of techniques that we can achieve this goal. But the general idea that we're trying to leveraging the generative AI and incorporate them with feed engine writing tasks, writing finding a site, and writing training signal, everything automated in simulation. So as a result, that we so the real goal we're trying to have this one click for any robot, we can propose endless task data for robot learning. So this is the demo. Actually, the fully automated generating in the Genesis simulation without too much human intervention. So you can see they can automate learning, kind of locomotion, they kind of data hand manipulation, they kind of very rich task. And the ultimate goal is we really want to build a kind of actually I call it as a generative robot agent that can automatically per task teach themselves the novel skill. And the thing happening in simulation, endless, automated. So this is my mission, that how we can really scale up the simulation learning in robotics. But there are actually the two critical challenges when we apply to the deformable object manipulation. The first thing that actually we all know that it's very hard to writing a reward function for deformable object manipulation. Okay, how we describe how the data has been deformed. It's really hard to use language to define the goal. And the second time, I think the challenge is that there's a lot of tasks in the world. The gripper might not be enough. To solve the challenge, we have some recent work. For example, in the first idea we have that we can using video model as the goal generation. For example, so this is work done by my student Ian. So basically, the idea that given a text description, pouring water from bottle. Okay, it's very hard to define the goal, like given images that you define task. But we can using a video generative model tell you roughly how to do the task. And the same way, like for the kind of pick up the spoon and score a wonderful sound, or pick up the nerve, cut the dog. So if you're using some video model, actually they can generating some reasonable path how to do the task, right? Then the idea came out how we can transform that kind of generative video to the robot policy. So this is Lucy about the paper we just submitted, actually trying to leveraging the generative video and turn it to and also transfer it to the robot learning path. The idea here that giving an intro scene with generative video, I'm using perception model to estimate their depth estimation, and then we put them in a simulation using this kind of trajectory as a guidance to optimize the policy learning. So for example, we first having this kind of image to video model for them, given this kind of making turning sandwich. So to spread kind, we have video model roughly tell you how to do that one, how the motion look like. You have perception, you have depth, and knowing the affordance, and also the rough trajectory for the human how to do that. We take them into a simulation as the initial trajectory, and then we can using different physics engine to optimize the trajectory and guiding the policy here. I show it here. And using this approach, actually we can teach robots to manipulate a bunch of different materials. For them, pouring this water, cutting tofu, and making this rope, supply the sauce, a bunch of different parts that using by leveraging the kind of generative video idea. And the second part that we still find that there's a bunch of tasks. Actually, robot gripper is also not enough. And in our current work, so our idea is that we can leveraging tool to do that fun. For the human do a bunch of tasks by using the tool. And we find one problem is that the human tool not necessarily be useful for robotics. For example, they kind of sister. You teach the robot doing the sister actually is very hard task, but in Meta you don't necessarily use that kind of very complex task designed for human. Yeah, and there's a bunch of robot designers that are trying to do the kind of manufacturing, design the software, design the kind of different tool, that kind of compliance. It's very manually designed. So my idea here is that can we automate the stuff using Genesis, using our model, how we can make the full pipeline automated. So in a recent work that we proposed called RobotSmith, so the idea that we're trying to do the kind of generative tool design for automated skill learning simulation. So the idea that we give a user input, we can use a large model to design the tool, edit the tool, and then we can actually joint optimize the tool and also policy that to guiding how to solve the task. For example, in this task, we're trying to we're trying to reach the cube outside the workspace, and we're trying to move it to the target pose. In this initial scene configuration, we actually ask the language model, okay, you can write this kind of scene configuration. For example, this kind of cube size, this position. We also give them the task set metric definition, so that you can calculate the position and trying to measure whether they reach the goal or not. And our RobotSmith pipeline actually, for the first part, we have the kind of critical tool design part. So basically, we're using collaborative vision language model to do the task. Basically, there will be a proposal that given this task description, he will basically propose this kind of geometry. And we also have another multi-agent critical framework. So in the task, so that he proposed a kind of cylinder to help to reach the cube, but it seems a little bit short with KLM. Okay, that's a bit short. So they can give the feedback to the LM, and then they can revise, writing that kind of writing a new primitive and generating a little bit longer to finish the task. So that kind of iterative agent framework actually enable us to and integrated with Genesis simulation, it can do the kind of automatically to design based on the feedback. And then we can actually using another language that we can plan the trajectory and finding which one actually can actually go. And in the final step that we can do the kind of I call it as joint optimization. We can revise the shape based on policies that we can do in the joint search of the kind of robot shape parameter and also the kind of policy. So we can do the kind of joint optimization. So the idea here that we also think that body and the brain are both important. So we need to optimize them together. So this is a rough idea that we are trying to push that have the kind of hardware policy co-design into loop using the Genesis. And as a result that we can fully automatically using the generative design, that kind of very interesting tool for them, this kind of lift bowl, they kind of fulfill the bottle stuff. And here is the real world result. And all the two actually all automated design using Genesis. You can see very interesting demo for them in that one. They're trying to pouring the water into this bottle. They designed that kind of very interesting shuttle hand tool. This all proposed by language model. We don't do any intervention, and they can grasp this approach and using the tool to pouring the bottle, so pouring the wind into this very small bottle carefully. And here we also in the last one we also trying to making that kind of pizza things using all the tools that designed automatically in the simulation. All right, to conclude my talk, so many people have been asking that what's the next for Genesis? So here I want to talk about something of my thought about Genesis. So I always thought that Genesis can be a Linux kernel for Embodied AI. So the two things actually we are trying to push actually I call it is Genesis build and Genesis runtime. So the idea of Genesis build is that we're trying to, and also there's another level that I think three things are very important. That's the first is the speed engine. The second one is symbolic program. They're using program to interact with speed engine using generative AI, that kind of coding part. And the third part, neural network, is kind of robotic foundation model. So in my vision that we are trying to building two things together. The first one we call the Genesis build. What is that? So it's more like a large-scale synthetic robot data generation pipeline that can really automate the full process in the simulation. And we can generate that kind of fully 3D 4D data. This that right now that can be go beyond of this kind of teleoperation idea. And the second part, actually, we are thinking is about the Genesis runtime. So this is essential. We think is a small size on-device foundation model that can close the gap between the simulation and real. In that time, we probably will mix that kind of Genesis simulation data and some real-world data and finding good mixture to train as well. So this is so we can do so, and also the training pipeline in my mind is also very similar to large model. Probably we're using the kind of data doing the first time imitation learning, and then you're doing the RRHF using the simulator to refine the policy. So this will be the roadmap for Genesis. Okay, so I think I'm a little bit running out of time. Any question?
Time for one question.
Great talk. So I'm very interested about your physics engine. So have you ever systematically compared your simulation with all these physical experiments?
So okay, that's a good question. So the question is that how Genesis compared with other simulations. Yeah. So on speed or capabilities, and also others, so probably.
Compare your simulation with your.
Okay, so the question is that how can we measure the sim to real gap? I think that may be the most correct here. So I would say that there indeed is a gap, and so I will see the gap for a couple of directions. The first direction that because that we build a simulation from first principle, that most from PD, there essentially has a gap, and also there will be a measurement between the accuracy and also the simulation speed. So the thing we are trying to do is that we're trying to make the simulation accurate enough for robot manipulation, but also make it running as fast as it can. And another idea, actually, we are trying to push that to using the real-world data to doing the kind of data-driven physics simulation. This is another pipeline we are trying to do. For example, we have the kind of reduced order approach that leveraging data to finding a low-dimension representation to make it running faster. And so this is from simulation part. But on the other side, that you probably have here a lot of approach about domain representation, physical parameter, mix that kind of stuff. So because you have a simulator, that kind of data problem can be either solved from data-driven approach or from the kind of large-scale data simulation. Yeah.
Yeah, so I think we'll move on to the next session. But yeah, thank you again.
Thank you.